Hi there. During this session I'll be very formally explaining some of the key concepts behind thermal physics for the IB. So there's quite a few definitions here and just consolidation of some facts which may seem obvious but have now been truly incorporated into thermal physics and the laws of. So let's begin. First of all, the definition of heat. Heat is defined as the energy that is transferred from one system to another because of a difference in temperature. Now, look in this example, if we had a hot beaker which is being heated up and a copper rod in between that and a cold beaker, then heat would naturally flow from the hot beaker to the cold beaker. And that's flow of energy is the idea of heat, I guess. One definition out the way. Definition of temperature now. Okay, so temperature is a measure of the average kinetic and potential energies of the molecules of the substance. Notice how that's a definition which doesn't involve the ideas of a boiling point or a freezing point at the moment. Temperature itself is this measure of average kinetic and potential energies. So that would be the formal formula which would be shown. Now in this situation we've got to recognise that for most monatomic gases the potential energy is assumed to be negligible, so it's assumed to not have an impact. So therefore, as we can see from the formula, the kinetic energy or the average kinetic energy of the particles is proportional to temperature only, and that's that key relationship. Next thing I'm talking about something called internal energy. Now what internal energy is, this is the sum of the potential and kinetic energy of all the molecules, and this is known as the system's internal energy. So what we think about here is that because there's motion and because there's forces acting between particles within a system, this provides it with what's known as the internal energy. So the internal energy is going to be the sum of all of the kinetic energy in the situation when we're thinking about a monatomic gas, because obviously the potential energy is negligible in that situation. Now here we can see the link between the internal energy and the temperature. Okay. So the temperature is related to the average kinetic energy of all the molecules, and whilst the internal energy is the sum of the kinetic energy of all the molecules. So there's another definition for us. Let's put some thinking to this now. So here's an example question. A swimming pool contains 28 degrees water at 28 degrees, and a cup contains tea, mostly water at 90 degrees. Those are the two situations. Which has the greater internal energy, the water in the pool or the cup? In which do the molecules have a greater kinetic energy, the pool or the cup? So think how I've just made those definitions, and we'll work through this. So, A, the total energy is associated with the thermal motions of the molecules, and the mass of the water has to be taken into account. So the water in the swimming pool will have a mass of the reason 10 to the 5, 10 to the 6 kilograms, and therefore the T's mass is going to be much, much smaller. So that means that the number of particles, although they individually have less kinetic energy, the amount of particles means overall the internal energy in the swimming pool is going to be greater. However, we continue this problem, the temperature which is directly related to the average kinetic energy per molecule in the substance. Now, we know that the temperature is higher in the cup of tea, and therefore the average kinetic energy of the molecules is going to be greater in the cup of tea. Another example now. What has more internal energy? 1 kilogram of steam at 100 degrees centigrade or 1 kilogram of water at 100 degrees centigrade? So this involves a little bit of thinking here, and it's not something I've directly mentioned, but the key thing to recognize here is that we're talking about water. So we're not talking about a monatomic gas in any way, and therefore, although their temperature is the same, which means that their average kinetic energy is going to be the same. There's another feature we need to take into consideration here, and that, of course, is their internal energy, so that's their potential. Now, the internal energy is the total energy of the kinetic energy and the potential energy. Now, as it's the same temperature, the kinetic energy is the same. But the steam will have a higher total internal energy, and that's because the particles will have a greater potential energy. Okay, so think about that, because when it changes from water as liquid form into a steam, what we have to do is break some bonds, and therefore we're increasing the potential energy of the substance. That's the key thing. Okay, temperature scales now. Now this is the measurement of temperature, not the abstract concept of temperature. Okay, so the measurement of temperature. Fahrenheit was based on the ability of farm animals to survive for extended periods without attention. 0 degrees Fahrenheit was the coldest, and 100 degrees Fahrenheit was the hottest. So that was the scale they had originally. Now, Fahrenheit, although still widely used in the US, Celsius and centigrade are more often used in scientific practice, and definitely in the UK. Here it's based on physical properties. So, water on the Earth's surface at sea level is 0 degrees as defined as the freezing point, and 100 degrees is defined as the boiling point. And what we have here is that between these two temperatures we have 100 evenly spaced degrees in between. There is a relationship between centigrade and Fahrenheit, and that can be calculated, although this isn't a calculation you'll need for the IB physics. On the whole, although we use Celsius and centigrade quite regularly in day-to-day life, what we find is that in science we use a different scale. And this is the absolute Kelvin temperature scale. Now this works from the fact that the pressure of gas is due to random collisions of molecules on the wall of the container. Okay, so they're bouncing around. Now that means that if we reduce the pressure to 0, we're also making sure we're reducing the kinetic energy of the molecules. So that means they'll have no kinetic energy. And this is what's known as absolute zero. And it's minus 273.15 degrees centigrade. Now, this is the value which temperature can't get any lower than. So this is a perfect introduction for a new scale, which is known as the Kelvin scale. The Kelvin scale actually sets 0 at minus 273 degrees centigrade. So let me introduce you to the Kelvin scale. The relationship for centigrade plus 273.15 gives us my Kelvin value. The details are the absolute or Kelvin scale is a true physical temperature scale. 0 degrees Kelvin is the lowest temperature that can be defined of any physical system. Kelvin temperature can never be negative, and thankfully the degree steps in Celsius and Kelvin are chosen to be exactly the same. So the size of a change of 1 degree of centigrade is the same as the change in 1 degree of Kelvin. Here's a couple of questions for you to think about. What is the freezing point of water and boiling point of water in Kelvin at 1 atmosphere pressure? There's a few more questions there. Take a moment, do the calculations. Here are our answers. Hopefully that's an easy enough set of conversions. And this kind of question often appears on the paper 1 of the IB physics, and this are the multiple choice questions. So final set of definitions now to think about. We recognise that when we look at an object and it's placed in contact with another object, they eventually tend to reach the same temperature. This is known as thermal equilibrium. This makes sense to us as what we observe in the world, but it creates what's known as the zeroth law of thermodynamics. If two objects A and B are in thermal equilibrium with a third object, then A and B are also in thermal equilibrium. So objects in thermal equilibrium have the same temperature. And what happens there is the motivation is that, as we know, that heat transfers from a cold object to a hot object. And at the point when all the objects are the same temperature, there'll be no more transfer of heat, so therefore this will be an equilibrium state. So there's a bunch of definitions for you, a few explanations. Hopefully this is going to help you moving forward the ideas of thermal physics.